Hello, everybody. Yeah, this is our seventh episode, and this episode is going to be a bit more interesting. And this deals with the blast analysis and simulations. So, this is a pretty interesting topic. So, this topic, uh, explores the possibilities from the positive aspect as well as the negative aspects. So the positive aspects include how the research and development, the optimization, the other possibilities, the reconstruction techniques, and studies for environmental purpose and study for safeguarding the ecosystems. So these are all the positive aspects of studying blast. The negative aspects are all connected with terrorism and war, etc. So let's start with what exactly the blast simulation is, the blast analysis is. This involves, using numerical methods, computational methods to predict the effect of explosions on structures and with the combination of various materials. This process uses certain softwares, and we know that there are several computational softwares and a few specific softwares used for blast simulation are all LS-DYNA, ABAQUS, AUTODYN, etc. The goal here is to understand how structures behave under blast loading. Say, like we have typical loadings like structural, thermal, fluid, etc. This also is a kind of loading, and based on these blast loadings and identify the potential damage or failure within the structure, and then optimize these designs for a blast resistance. So which means try to understand the structural failure for blast, and also try to understand the design possibilities or the material selection possibilities for resisting the blast. Okay, so this can be done using numerical methods, and this can be done using uh, empirical methods also, or experimental methods. So now let's try to understand what exactly a blast is. Blast analysis aims to understand the physics of explosions, which includes the generation and propagation of shock waves, pressure waves, and impulse. So shock, pressure, and impulse. These are the three different aspects for a explosion. Explosion is nothing but it's a physics. This includes multi-physics basically. It's not only on the shock loads or the pressure waves. It also depends on. It also accounts for the thermodynamic feasibilities, change in temperature, change in energy, change in chemical kinetics, and it also involves change in energy from one form to the other. So a blast always has a light as well as a noise. Okay, so now here we try to understand the phenomenon. What is the blast phenomenon? So it's basically it aims to understand the physics of explosions, which includes the generation and propagation of shock waves, pressure waves, and impulse. Now, how do we design blast loads? How to model the blast loads? Various methods are used to model blast loads, including empirical formulas like the Kingery-Bulmash model, where the pressure time functions are taken into consideration, and compressed balloon models. These are the two different models with which a blast simulation can be uh, performed. So one is the Kingery-Bulmash model, and the other one is the compressed balloon model. Now let's see, how the structure is going to respond for these kind of uh, loadings. So that is the pressure loading. Then you have the shock waves, and then you also have the impulsive loads. So these are the three different kinds of loadings that comes. So in structural response, the analysis also involves simulating how structures respond to these blast loads, including deformation, stresses, and potential failure modes. So potential failure modes is nothing but, we try to perform a natural frequency, we try to extract the normal modes, and then from the normal mode simulation, we go for random response simulation or frequency response simulation. And we also give a specific range of frequency, and between this frequency to the other frequency, try to extract so many values. And this will be for a period of, say, about 100 seconds, or maybe about say 50 seconds. And within this time, what exactly would be the responses, and how are the stresses going to be, how the deformations are going to be. So all these studies are done. So the pressure time functions are taken into picture, and based on that, we will try to identify what are all the stresses and what are all the deformation pattern. Now, let us say, like, we want to simulate a specific blast, and now for that, as I told you earlier, we make use of software like LS-DYNA, and it's a widely used finite element analysis software, and that can model complex dynamic events like explosions. And ABAQUS, of course, it's an explicit dynamic system. It can handle explicit systems and implicit systems. Okay, and this is widely used for simulating blast. So I had given you an example in the previous session. I mean the video. I discussed about the simulation of the bird hit on a gas turbine, that is the jet engine. I also gave an example of a missile or a shell that comes and falls on a battle tank, and how the battle tank hull ruptures or tears off. So these are all two good examples that speaks about explicit dynamics. Okay, so these are all functional oriented. It can be force based, it can be frequency based, etc. Now, as I told you, like how LS-DYNA or AUTODYN are specifically used for simulating blast. So high speed dynamic events. So high speed, that is within very small time, okay, dynamic events or dynamic activities that happens. Okay, so those are all considered to be explicit in nature. And we make use of coupled Euler-Lagrangian methods. Coupled Euler-Lagrangian (CL) method. So this is the one specific numerical method that is adopted in these tools like LS-DYNA and ABAQUS. Okay, where uh, uh, dynamic events, very high speed dynamic events take place. So impulsive, based on or corresponding to the shock wave. Say, for example, there is a bridge, and on the bridge there is a train which is moving at a speed of, say, about 400 or 500 kilometers per hour. That's quite a speed. And when this train moves from one end of the abutment to the other end of the abutment, that is, one end of the bridge to the other end of the bridge, in a very short time, there will be oscillations, like 75,000 CPC, cycles per second, to 1,25,000 cycles per second. So this is in fact considered to be a very high speed. Okay, and it's a dynamic event. And these loads can become shock loads, and these shock loads can destruct or damage the structures. That is, the bridge can destroy. Now, in order to reduce the shock load or to make it shock proof, these bridges are uh, perfectly bound, or it's rested on some neoprene dampers or pot from PTFE dampers. And now these dampers, okay, have hyperelastic materials, say like your rubber, neoprene rubber, etc. It also has Teflon, nylon, etc. So making use of these kind of hyperelastic, viscoelastic materials, uh, these shock loads are tried to dampen. And apart from these bearings, there will be shock transmission units or lockup devices, LUD. These devices are nothing but it's similar to your shock transmission or shock absorbers in the vehicles. Okay, so the only difference is it has movements, the stroke length from both the length. So, whatever load, when the train moves from one end A to B, the shock loads get transferred from B to A. Now, because of that, there should be a counter movement, not moment, counter movement in the stroke length, in the shock absorber. Okay, so there are very high viscous materials which is used within the dampers, and these dampers are able to convert the high viscous lubricants like silicone gel or silicone grease, and these silicone grease uh, is transformed from a highly viscous jelly-like substance to uh, liquid, fully liquid system. And now, because of the phase change or the transformation, there will be change in energy, and thermodynamic parameters are included, and there will be some heat also. Okay, so this is how the energy, the shock loads are conservated. So it safely gets transmitted from the bridge deck to the pier, and from the pier wall to the pier cap, and from the pier cap to the piles to the foundation. So this is how the shock loads are transmitted, and when these shock loads are transmitted, they change. They change the phase of the silicone grease from high viscous lubricancy to liquid. Okay, and because of that, there will be a change in energy also. There will be some heat generated. Okay, so that's why we call it as energy management devices or dampers. Okay, so these are all explicit systems, and now these explicit systems needs to be simulated, and this is quite possible using softwares like AUTODYN, LS-DYNA, ABAQUS. So they make use of coupled Eulerian Lagrangian method (CEM). And what are the key aspects of a blast? So that is something which is very important. The size of the elements in the simulation, the mesh significantly impacts the accuracy of the result, especially for shock wave propagation. See, finite elements, the biggest problem is about the size of the elements. As I told you, any geometry can be broken down into several well-defined geometries. Say, for example, let us say the cross section of the shock transmission unit. It is very similar to your shock absorber. So that will have a cylinder, it will have got a piston, and then there will be some two or three or four compartments, and one end of the compartment is fully filled with the silicone grease, and then when the stroke length increases and when the piston tries to move forward, the silicone grease from the innermost compartment is tried to squeeze to the other compartments through certain voids which is kept inside the compartment. So on the compartment there will be some grooves, and through these grooves, the silicone gets injected from one compartment. That is the compartment from one end to the other end. So in between these compartments, it will transform. So from grease or silicone grease or highly viscous uh, liquid, it will try to become liquid, and because of which there will be a temperature change also. Now, this particular mechanism can be designed from, because since there is a phase transformation involved, okay, phase change involved, we try to model it as a fluid structure interaction (FSI). Okay, that is nothing but it's like You treat it as an explicit system. Okay, so using finite elements, uh, these regions, the groove that is on the compartment, there will be very miniature grooves, and the silicon escapes through these grooves from one compartment to the other compartment. So when we model it, when we go for the finite element model, when we develop the finite element model, these grooves, okay, are to be designed in such a way that the mesh size, the element size needs to be proportionately managed. So if the biggest element has got a size, the smallest element there should also have a proportionally small size. Only when the number of elements there are more, the large ordered elements, only then we will be able to get quite a good accurate results. So usually what we do is we try to model it using plate elements like quad, and from the quad we extend it. We go for hexahedron brick elements, and like some regions we even go for pyramids, and tetrahedrons will become more stiffer because they are all the generic elements formed out of triangular elements. So they are all quite stiffer. So it's always better that we prefer a quad element or the extension of quad elements like our hexahedron brick elements and uh, wedge elements, etc. Even wedge is also, that also carries the genera of a triangular element, causing stiffness. So this particular model should be lesser in stiffness, because if stiffness parameters are high, the results, the accuracy also will become very less, and then the time taken for convergence, the solver convergence is also more. Okay, now what we do in performing these simulations, because these simulations involve quite a lot of materials. There will be steel, there will be concrete, there will be viscous materials. Okay, sometimes there will be fluids whose Reynolds number is much higher. Sometimes there will be fluids which is like jelly, or it can be like highly viscous. So since various type of elements, sorry, materials are involved in this, the accuracy needs to be kept. Say for example, uh, experimental data. We get the experimental data. So experimental data, we have uniaxial shear values, biaxial shear values, and triaxial shear values. And now, apart from that, we also have the material properties like your Young's modulus, and sometimes if the material is non-linear, like the hyperelastic materials like the rubber, etc., or like EPDM. So these kind of materials will have material properties along all the three planes. So X, Y, Y, Z, ZX. There will be a lot of changes. We can't even call it as anisotropic material. Sometimes it becomes orthotropic material. Okay, and isotropic materials are those materials which will be having the properties same in the same direction, in in the same plane. Okay, so most of the isotropic materials are what we use for general purpose analysis. Until and otherwise, these materials are specifically, like notified. Like this particular material is going to be used here, and this particular material has got a viscous flow, and that will be having a transformation, phase transformation. So in such cases, we give the right material. We also give the right properties. Okay. Now, what are the reasons like we go for this? Okay. One is for applications of protective structures. As I told you, when the architect or the structural engineer designs and develops an apartment, the apartment, let us say it has got more than 15 stories, or say 30 stories. Now this is going to be like a skyscraper. So most of the structures are going to be designed either as a portal frame or like beams and columns, and sometimes it will be completely steel structures. And now steel beams and column sections and channels or girders, which is bolted, and the in between panels. It can be wall panels, the shear panels, or it can be even concrete, or it can be even plywood, or polymers. Okay, and sometimes there will be glass claddings also. The region, those regions where it is exposed to light. So we want window. Window is a specific region in a structure, in an apartment or a house, where the window is kept separately for the light to enter inside. Okay, and to have a view. So now that particular region is covered using glass. And now this particular glass should be very strong enough and safe enough to withstand even earthquake loads, seismic loads. So all these kinds of materials, which are generally not isotropic, anisotropic or orthotropic, okay, are used in the simulation, especially in the blast simulation. So they perform the blast, they check whether the structure is safer. Now, if it is not safer, they will try to identify an alternative material. Say glass alone may not work. So instead of that, what they do is in between two layers of glass, they go for some uh, glass reinforced systems, or wool reinforced systems. Okay, so there are companies across the world which is doing it. This is not only used for the residential purposes, it is also used for defense purposes, defense vehicles. So these defense vehicles, when moving on, rough terrains and all, it is subjected to shock loads. And even when the enemy shell is fired and it comes and falls on the armored vehicle, that is subjected to damage, explosion. So in such cases, these glasses are to be taken care of. It should be a special graded material, and these special graded materials are generally called bulletproof materials or explosion-proof materials. Okay, so that is one of the areas, and then industrial safety. Industrial safety is something which is very important because industries, they have a lot of chemicals, corrosive chemical, non-corrosive chemical, sometimes reactive chemicals. It can also explode. Okay, so now if there is an explosion which is caused in the boiler or in the pressure vessel, so that is going to impact the structure also. Okay, and that is going to be fatality, and there is going to be a lot of injuries also. So in order to prevent that to happen, and in order to keep these kind of fatalities or accidents away, the structures are all designed. Virtually, it's handled using finite element software, and then they perform the structural simulation, and based on which they try to arrive at the optimized result. Okay, so now that is one important thing, and then uh, apart from these things, the generic ones, these are all the legal based systems. So why I say legal is these are generally considered as a part of the design because they don't go for a very high factor of safety materials, sorry, design. Instead, they keep the factor of safety nominal, and keeping the factor of safety nominal, they try to do some, they fiddle with the materials, the material properties. Okay, so using very smart materials like the carbon fiber or glass fiber. Okay, these are all smart materials. So making use of smart materials and then making composites out of it, and then making use for the structures. That is, what do you call? That's called as a highly optimized structure and a smart way of design. So these are all the the legal aspects of explosions. That is blast analysis. Now, illegally, what happens is there is a war, and because of the war, there are the enemy territory. They are firing continuously missiles or shells or rockets, and then it is always possible that it can come to the town and can hit the apartments. It can blast the apartment. There is going to be a lot of fatalities, etc. So now that particular ecosystem has to be designed. So designed not only for shock-proof or explosion-proof materials, that is structures, It also needs to be assessed for environmental hazards, safety. So it should be free from temperature. When these kind of missiles or rocket attacks happen in the city or the town, there will be a huge rise in temperature in the environment. Okay, so let us say the atmospheric pressure is there, and there is a ambient temperature. Now, what happens is the ambient temperature will rise. It can rise even exponentially when there is a shell attack or a missile attack. Okay, so now that particular area, the urban area or the town area, needs to be properly uh, designed. There should be, enough space between two different structures and two different apartments, residential apartments, and there should be enough space between two different, uh, you know, like uh, uh, commercial buildings. It can be, some factories or anything like that. So in between the factories, there should be some greeneries, and now these greeneries will be helpful in reducing the ambient temperature, the environmental conditions, etc. So all these things can be pre-designed, and then the with the proper planning, they will be able to establish a proper ecosystem. So now, for today, let me just conclude here, and there will be a very specific video on blast. So other than this, there are many other videos, and that's what I told you in my previous videos also. Like if you subscribe this particular channel, you will be able to see all the other videos. You'll be able to see videos on blast. You will be able to see videos on fluid slush. You'll be able to see videos on aerodynamics, external, both internal and external. You'll be also able to see videos on durability, noise and vibrations, acoustics, lots and lots, frequency responses, random responses. So I have specifically mentioned a case study, and based on that case study, there will be some simulations performed. Okay, so now I am trying to make these sessions very interactive and very simple. I don't want any numerical calculations or numerical simulations to be, uh, performed or conducted, because it becomes like more or less like a training session. My intention is not a training. I just want to share the case studies, the projects that I've worked on for the last 27 years in various industries. I want to share my experience, and I want to give you some practical know-hows, the tips with which you will be able to, whenever you encounter few problems like this, you will be able to easily counter-attack, and then you will be able to come out with a proper solution for that. And apart from the practicing engineers, this will be an absolutely good session for budding up engineers, those who have completed your engineering and planning to take up some good jobs in these areas where you can contribute very much extensively in the digital simulation field. Now, digital simulation with artificial intelligence is the key, the core competency in every engineering, no matter it is aerospace, automotive, or heavy engineering or structural. Okay, so there is a, certainly there is a good amount of what do you call, induction. There is a good amount of containment of artificial intelligence in these areas. So here you will be able to understand how artificial intelligence and the digital simulation softwares are going to change the product development industry. So this is called generative AI, generative artificial intelligence. So making use of generative AI, how optimization, the design optimization, design of experiments can be carried out. So earlier, as I discussed, doing optimization used to be a nightmare. N number of iterations. Let us say n is equal to 100 iterations to be performed, even before a product launch, which used to consume months together in a very powerful supercomputer, which used to be only available with the government lab facilities. Okay, so today we have GPUs and many advanced systems, parallel computing, high performance computing, and everything. Which has taken over, like companies like Nvidia. has put a enormous effort in uh, producing these kind of systems. So which is extensively used for generative AI, and especially for fields like aerospace, automotive, weapon warfare, etc. And this is how the future is going to be. Okay, so I request you to subscribe the channel so that you'll be able to see all the videos, and it will be very interactive for you. Go through the videos, and whatever you feel you want to extrapolate and discuss further, you can put a comment into that, and based on those comments I will try to create a separate session only for that, and then I will try to make it more interactive. Okay, so have a wonderful day, and let's meet in the next session. So thank you very much.